7.4, the angle bisector theorem, and we're going to do a little bit of an introduction to the Pythagorean theorem, which we'll be delving into much more next chapter. Objective: students will be able to use the angle bisector theorem to solve for missing parts in triangles. So here's the angle bisector theorem in words. Here's a picture. Here's the basic formula. Of course, so this formula is only relevant to this picture. If we were to label this maybe C and label this little b, and then we could just call this x and y. Another formula you can make, and it's really pretty simple, is you just put the side over a part of the side that's being cut by the angle bisector. See, an angle bisector just means that it's being cut, an angle is being cut into two equal halves. So you could see how if you follow this line that cuts the angle in half, it also cuts this opposite side in half. And so basically you could write this equation as c over x equals b over y. So that's another way of looking at the same equation. See, the side over its corresponding part here, side over corresponding part. And so you could write that equation. And like with all ratios, you could also flip it. You could write it as x over c equals y over b. You could do that as well. Whatever is most convenient for you to solve it. And so the actual angle bisector theorem itself says that an angle bisector of an angle of a triangle divides the opposite side into two segments that are proportional to the other two sides of the triangle. So here's the opposite side of this angle, and here's the two segments that are proportional to the other two sides of the triangle. And so y is to b as x is to c, or you could say segment DC is to CA as BD here is to AB. Now, important to recognize, these letters are not consistent, right? If I had a triangle that was named, I don't know, PQRS, well, actually the triangle would be PQS, but if that was an R, then this formula is totally different, okay? So you need to think about not necessarily memorizing these formulas, but memorizing the pattern that the side goes to its corresponding part and this side to this corresponding part. Side over part, side over part. Or you could do part over side, right? Like I did here. It doesn't really matter, just as long as you know these are related and these are related. So let's use it, okay? Let's use it here in example 1. And they're actually talking about the triangle that's right above us, so that's convenient. And it says AB is 5. So AB, that's this side, is 5. AC is 6. BD is 4. What is the length of CD? Well, let's just go ahead and use this formula right here and plug it all in, right? So we know that AB is 5 and AB, according to this formula, is the top right, or BA is the same thing as AB. And we know that AC is 6, or CA, right? AC or CA is the same thing. So I'm going to put the 6 over here. And we know that BD is 4. BD and DB, same thing again. So I'm going to put a 4 down here. And then what we're trying to find is CD or DC, which is this part. And since in the drawing I labeled it Y, I'm going to just label it Y here as well. And what I also want to do is I just kind of want to color code this so you guys can see it, all right? So they're saying that AC is 6. There's the 6. We know that AC is the same as that. And according to my drawing, AC is this side. We also have AB or BA, which is 5. And that's this side here. And then we also have what they give us, BD, which is the same thing as DB, which is this side here. And so we said that that's 4. And then finally, the Y, the Y, the Y, right? That's the CD that we're trying to find, or DC. You could say it either way. That's why the letters are flipped in the formula as opposed to the problem. Okay, well, now that we have the equation written, now the math is actually pretty easy. It's not hard at all. But we have to understand how to set this up correctly. Typically, when I'm doing a proportion problem or a ratio problem, I like to have my variable on top. So what I would actually do is I would write it as y over 6 equals 4 over 5. And you're allowed to do that. As long as you flip both sides, That's totally allowed. You could flip, as long as you flip both sides, it's fine. So I did that. And now once I flip it, I realize, okay, all that's happening to y right now is it's being divided by 6. So a really quick and easy way to solve for y is to simply just multiply both sides by 6. That cancels that out, and that would give me y equals 4 times 6 is 24, so I just have 24 over 5. I would leave my answer just like that. But if for whatever reason they wanted a decimal, you could plug that in your calculator and you'd get that that's equal to 4.8. And there you go. That's pretty simple, pretty straightforward. We've used the angle bisector theorem to solve for the missing part, which in this situation again was CD or DC or Y. I called it all three things just to see how you might see it labeled differently in different problems. Now I want you to use that same pattern, same formula, but notice the triangle is a little bit different. They happen to use the same letters here, A, C, B, and D, A, C, B, and then D. So it's a little bit different, but one of the things here I marked them, the two angles as congruent. That tells us it's an angle bisector. Well, here they don't do that. What they do instead is they just say, oh, this is theta and this is theta. So they're saying these two angles are the same. So that is the same thing then as saying, oh, look, this angle is the same as this angle. They're just giving you a hint that, hey, these angles are the same, therefore you can use the angle bisector theorem. And so the triangle is rotated now, right? See, this is a common thing that kids get confused with. You got this angle up here, and now the angle's over here on the side. So that doesn't matter. Remember, it's just the side over the part, the side over the part. So here's your side, here's your part, here's your side, here's your part. But I'm gonna let you guys see if you could set it up and solve it, and then you're just gonna pause it, try it on your own, and then check back when you're ready. Okay, hopefully you got the same thing as me, but I want to walk you through a couple things. I went ahead and just, since I'm trying to find this question mark, I went ahead and just labeled it X. Just makes it a little bit easier to play with. And then instead of putting the sides on top, which is what the formula says, remember this formula said like it put CA, which is the side, on top. I said you could also put the parts on top. You could just flip it. So I went straight ahead and flipping it since I knew the thing that I was looking for was the part, not the side. So I put the parts on top and the sides on bottom. And once you do that, it's pretty easy because now the x is on top. All that's happening to the x is it's being divided by 4.4. So you simply multiply both sides by 4.4. This gives you 18.04 on top and 6.8 on bottom, which when you divide is approximately 2.65. In this situation, you would not leave it like this because you have decimals within a fraction, which is not proper. Here above, we just had integers on top and bottom, and so you could totally leave it like that. But this is, you would never leave it like this, so you just write it as 2.65. This obviously, this is a decimal answer that keeps going, and I don't even know if this is a nice, neat fraction or not, but there probably is some neat fraction you could write it as. But in this situation, just plug in your calculator around to 2 decimal places or whatever they ask. If they don't ask, I always just do 2 decimal places. Or if they don't specify how many decimals, I use 2. But this is, that's all there is to it. Put in the decimal answer and you're good to go. Okay, so that's the angle bisector theorem. But now I want to talk about the Pythagorean theorem. Now the Pythagorean theorem is something you should have seen before. It shouldn't be new to you, but I just want to go over it again. In a right triangle, and this is huge, it only works in right triangles, so you may want to just like highlight that or something. This is only true in right triangles, and by right triangles I mean that it has a 90-degree angle. The square of the legs added together is equal to the square of the hypotenuse. So a squared plus b squared equals c squared. Now, another thing that's important. Often I see students do this. The thing that's all by itself in the Pythagorean theorem, the equal c squared, has to be the long side. The side that's directly opposite of the right angle. We call that the hypotenuse. It has to be that. If you put like the A here and then the C here and then the B there, this will not work. This will not work. Another thing that I see students do that's a big no-no I want to talk about real quick is when they go to solve this, and we'll work this out in a second, is they're going to take a square root and they see, oh, square root, and they think, oh, well, the square roots cancel out. This is just A plus B equals C. That is absolutely not true. That does not work, and I'm going to prove to you why here in just a second. let's use some really simple numbers. Let's use something like 3 squared plus 4 squared equals 5 squared. I know that works, right? Because I've done this lots of times, but 3 squared is 9, 4 squared is 16, and 5 squared is 25. It works out perfect. 9 plus 16, 25 equals 25. Perfect. Those numbers work. But let's do what I was proposing earlier. Let's plug in a 3, let's plug in a 4, and let's plug in a 5. And let's take the square root of both sides. If we pretend, and this is why this doesn't work, there's actually like imaginary parentheses here, but if we pretend that those aren't there, okay, so just pretend those aren't there, and we think, oh, this will just cancel it out, okay, we're just playing with this, and I say, oh, that cancels that out, and this cancels out, you would have 3 plus 4 equals 5. Well, 3 plus 4 is 7, and there's no way that 7 equals 5. So we can see that that is not an accurate step. So don't do that. We've now talked about it in the video. I've talked about this in class before, and hopefully we don't make that mistake, but it's a very common mistake. Instead, we can do it the right way. So let's go to example 2. Let's actually play with this now. So in this triangle over here, they're telling us that A is 4, B is 6. They want us to find the value of C. So we just use this formula. I like to copy the formula down. You don't have to, but I like to just have the formula right in front of me. Then I'm going to plug in a 4. I'm going to plug in a 6. And I'm just going to leave a C there. Okay, so we could see where all that came from. There's my 4, there's my 4, there's my 6, there's my 6. Okay. Well, 4 squared is 16, and 6 squared is 36. And we don't know what C is. 16 plus 36, what is that? That's like 52. And then we just take the square root, take the square root. Well, on the right side, we just have a C, but on the left side, we have the square root of 52. We would not leave it like that. We'd want to simplify it down. And it just so happens, like we've played with all year, there are some perfect squares inside of 52. In fact, you could think of this as the square root of 4 times the square root of 13, because 4 times 13 is 52. And the square root of 4 is 2. So you would write this as 2 square root 13. And that is a fine answer. But let's say they were asking for the decimal, then I would plug this in my calculator, and I would just say 2 times the square root of 13. That is approximately, I just put that in my calculator, that is approximately 7.21. And then you could kind of check to see if you did it right, if you did this right, because I got 2 square root 13. I could also plug this in my calculator, and I could type in square root 52, and you should get the exact same thing, 7.21. And so we've used the Pythagorean theorem now to solve for C. All right. I have both the exact answer. This is an exact form, and this is the rounded. And that's a good practice for you to be able to do both. All right, let's go to the next page.